friends, in this lecture, which is the fifth lecture in module 3 of HSC practices, where we are focusing on accident modeling and risk assessment and management. We are going to talk about chemical explosions. Interestingly, any explosion we know releases energy suddenly. This results in what we call peak over pressure, which can cause damage. That is what we have seen. Interestingly, in case of chemicals, the energy released in chemical explosions can be computed using standard thermodynamics. The heat of combustion is used as mode to assess the explosion strength. So, the exploration strength or explosion strength is assessed through the heat of combustion in case of chemical explosions. From the past studies in the literature, it is evidently seen that the explosion energy differs by about 10% from that of the value computed from heat of combustion. So, if you are able to estimate the explosion energy using the heat of combustion without using the standard laws of thermodynamics, the error resulting will be about less than 10%. Therefore, explosion energy is generally determined in different techniques. When we talk about physical explosions, which essentially come from mechanical systems, the source is a mechanical system. So, unfortunately, no chemical reaction takes place. In this case. So, in that cases, energy is obtained directly from the energy content of the contained substance. So, energy released is obtained directly from the energy of the substance which is contained There are common approaches available in the literature which can be used to estimate energy release caused by physical explosion. Different methods used to compute the energy release. One is what we call Broad's method. According to Broad's method, the energy release will be equal to P2 minus P1 by nu minus 1 into V, where P2 will be the bursting pressure, P1 will be the atmospheric pressure, nu is a heat capacity ratio, which is known for every chemical, and V is the volume of the vessel. Second method could be isentropic expansion method. According to this method, the energy release can be found out by this equation P2V by nu minus 1 of 1 minus P1 P2 nu minus 1 by nu. The third method could be isothermal expansion method. According to this method, energy release is given by natural logarithm of P2 by P. Of course, the fourth way is based on the conventional laws of thermodynamics. When we talk about dust and gaseous explosion, because they can also cause explosion. Interestingly, for a gas, molecules are smaller and have a well defined size. For dust particles, the size is varying. Okay. This variation in magnitude is larger than the molecules. Therefore, we used to calculate what is called Kg and Kst. So, Kg is called deflagration index for gas. Kst is called deflagration index for dust. So, G stands for gas and St stands for dust. Interestingly, variation in pressure which is caused by the dust or gaseous explosion with respect to time is shown in this figure. Please pay attention to the figures shown on the screen now. The left side figure shows the variation of pressure for gas with respect to time, whereas the right side figure shows the variation for dust. So, the pressure gradient is different in case of a gaseous release or an explosion caused by gas compared to that of a dust. Let us quickly compare these two and see what are the observations we can make. We are trying to write the explosion damage caused by gas and dust. Okay. So, let us say gas dust explosion. The first difference one can say is the dust particles, size of the particles vary, whereas in gas more or less they are smaller in size and well defined. The second could be in both the cases the maximum pressure reached because of explosion release energy is same. Okay. In both cases it is same. You can see from the figure, in both cases P max is approximately about 8.5. However, the gradient dP by dt in this case for dust and in this case for gas, they are different. I can say this is more or less instantaneous, but this is more or less gradual. This occurs without any time delay. This occurs after significant time delay. Please pay attention to the curve shown on the screen. So, the right hand side curve shows the pressure variation in terms of time for the dust explosion. You can see when the dust gets injected, there is an injection time, again the pressure comes to 1 atmospheric. So, there is a delay time, and at this point when ignition occurs it picks up to the peak. So, the time taken for the dust explosion to reach the maximum is much more compared to that of time taken by a gaseous explosion to reach the same maximum absolute value, because this is more or less instantaneous, does not have any time delay, whereas this has a time delay. In this both the cases more or less it can be a same gradient, but it has a time delay. Therefore, dust explosions are caused after significant time delay, which can be easily controlled if the control mechanisms are in place to mitigate or to control the explosion phenomena happening in the process industry. So, we have been talking about explosion damage estimate. Because one is interested in doing the damage rather than actually knowing how to model the explosion. We all know that there are certain facts which I have understood now. One, explosion generates a rapid rise in pressure. That is the first order of understanding to know the damage caused by explosion. This is essentially produced by shock waves. As the wave propagates, it causes damage along its path to objects along its path. It has a cumulative effect. One caused because of pressure reaching peak over pressure value. Second is due to negative pressure. Negative pressure results in suction effect. which is quite dangerous and very vulnerable in terms of damage. On the other hand, the damage caused by dust and gaseous explosion, the damage caused by dust and gaseous explosion depends on the maximum pressure reached. Out of these two, time delay will be there for the dust explosion. Therefore, damage caused by dust explosion can be controlled with effective design, but damage caused by gaseous explosion or instantaneous and rapid release of energy occurs, therefore, they are more catastrophic in nature. Of course, they also depend on other factors, velocity of propagation, which we already saw. It also of course depends on environmental conditions. So, there are two cases here what we saw. One is detonation, other is deflagration. Both are process of explosions. Deflagration can result in rise in pressure which is approximately 8 times of the initial pressure, whereas detonation, the increase in pressure can be even more than 8 times. P initial. In both the cases, the rate of pressure depends on mixture characteristic, degree of containment, of explosives, and the environmental conditions. Which includes velocity of propagation, wind direction, etc., as said by Roberto and Mauro, 2008. Please pay attention to the figure shown on the screen, which has already been discussed in the last lecture. Just for completion's sake, we are referring to this figure back again. This shows the pressure variation with respect to time. So, the peak overpressure, which occurs instantaneously in an explosion release, causes damage, followed by which the damage is further caused by the negative pressure. Area under this curve will actually indicate me the damage extent. If we really wanted to prevent the fire and explosion which can occur from any flammable mixture, so prevention of fire and explosion from any flammable mixture depends on how can you reduce the ignition sources or the presence of ignition sources. How to ensure safe design procedures so that electric short circuiting, things like that can be avoided. One can also think of how to reduce the flammable inventories. One can also think of how to replace flammable construction materials with alternate composites. One can also think of how to reduce the temperature and pressure. In fact, we should say, instead of reducing, how to release excessive temperature and pressure, which is built during the process. You can use pressure relief valve, you can use temperature sensors, you can have coolant circulators, etc. So, one can also look at different fire and explosion preventive measures. Okay. So, these are some of the, based on this one can design a variety of fire and explosion preventive system, which anyway we will see in the next lecture. So, in this lecture we try to understand what would be the energy release computed for chemical explosion, dust and gaseous explosion, what would be the difference between two types of explosions like detonation and deflagration, what are the factors which should be focused if we really want to work at prevention of fire and explosion from any flammable source of material, which could lead to ultimately how one can design a variety of fire and explosion preventive systems which can be in place in order to mitigate risk arising from fire and explosion, which is a very important segment in terms of offshore industry is concerned. Thank you very much.